So in this video, you're going to look at uses of proportions in geometry. We're going to explore similar figures and we're going to revisit scale drawings. We're going to do a lot more of the application piece in class, but I just want you to be familiar with how to set up the proportions for similar triangles and then just making sure that you remember how to do so for scale drawings as well. So we're going to look at some uses of proportion in geometry, and the first use is similar figures. So in order to discuss similar figures, we have to figure out what the word similar means when it has to do with geometry. So similar shapes, whether they be triangles, rectangles, whatever, have angles that are congruent. So the angle measures are equal of these triangles and the sides are in proportion to each other. So you can set up ratios of similar sides and those ratios are going to be equal to each other. So if we look at the diagram, we notice that it says that triangle ABC is similar to triangle DEF. So that little squiggly symbol means similar. We visited that for the first time when we were talking about congruency in like alternate exterior angles and alternate interior angles, and we looked at how the congruent symbol was an equal sign with a similar sign. So we can say that angle A is congruent to angle D. And the reason that we can say that is because the way that these shapes are similar is dictated by the order of the letters when they are named. So if you look at these two triangles, they have different orientations. One of them is right side up and the other is upside down. So we wouldn't really know what angles or sides relate to each other unless we looked at the figures, at the wording. So the similar statement tells us that ABC is similar to DEF. So if I have triangle ABC, and I know this is just a sketch, it means since the A comes first that the D and the D comes first, that the D would have to match up. So the D and the A would match up, the E and the B would match up, and the F and the C would match up. So it's almost as if it may be beneficial to you to re-sketch the drawing in a way that shows them in the same orientation. And the reason that's going to be helpful is because then you can compare apples to apples without kind of twisting your head or making it confusing. So DEF, the D and the A have to be in the same position, the B and the E have to be in the same position, and the C and the F have to be in the same position. So if I were to create these figures with the same orientation, then I can say, hey guys, what's the value of ED? What's this side measure that I'm not really quite sure of? And you would be able to say, oh, okay, well, I can say that 6 over 10, because AB is 6 and CA is 10, equals, I don't know, over 5. Because this BA and ED match up because of the way that the letters are. And CA and FD match up because of the way that the letters are. The F comes last, the D comes first, the C comes last, the A comes first. So you know those sides are going to be the same. And then when I solve this proportion, I got that x equals 3, which is probably what most of us figured out just by saying, oh, 6/10, that reduces to 3/5. So that means x would be 3 because proportions are just equivalent fractions. So just know that when writing a similarity statement, the order of the letters tells us everything, like everything. It's really important. So if you look at diagram 1, this one, you're going to see that you're going to be like, hey, Ms. Lameda, there are no similarity statements. There are no letters. Like nobody's telling me how they're similar. They are. But what they're not showing you is letters. What they're showing you is lines. So when you look at the two angles, the two lines or the single line, what that's showing you is that that angle and that angle are congruent. And that angle and that angle, you can't see it, but are congruent. And the important part of that is that then you can say, okay, if I know what angles are congruent, then I know that my shapes are in the same orientation. They're the same way on the page. So I could really put the bigger triangle and the smaller triangle inside of each other and say, okay, well, that's 4 and that's 16. And I know that because my double angles are matching up. The double angles, the double lines. The double lines mean that they're equal. And the single lines are the way for you to tell the difference between these two angles being equal and these two angles being equal. What that does tell me is that 5 doesn't match up with anything and 6 matches up with x. So it's telling me how these triangles match up. So then I can go through and I can say, okay, well, 4 matches up with 16, and 4 is on the smaller triangle and 16 is on the bigger triangle. The only other pair that I know are 6 and x. So I just have to make sure that I align 6 as the smaller triangle and x as the larger triangle. And then from here, I can either reduce my fraction first to 1/4 equals 6 over x, and that would just make my multiplication and division a whole lot easier to find out that x would be 24, because even if I did the multiplication with the original fraction, then I would get, with original proportion, I would get 4x equals 96, and 96 divided by 4 would be 24. For the second similar figure example, I'm given angle measures or angle similarities, so I know that angle D and angle G are congruent, and I know this because of the 3 lines, and I know that angle A is congruent to angle E because they both share 1 line, and then I know that angle B is congruent to angle F because they have 2 lines, and those lines tell me the pairs of angles that are similar to each other. Using this information, I could write a triangle similarity statement, and I could do it so many different ways. But let's just start with, I could say that triangle ABD is similar, and then I would be able to look at the other triangle and I would say, okay, what would match up with A, what would match up with B, and what would match up with D? And A would be E, and B would be F, and D would be G. So triangle ABD is similar to triangle EFG, which means that I could look at the triangle now and I could say, okay, what pair of information do I have for 2 similar sides? And the only 2 similar sides that I definitely for sure know are that AB is 4 and EF is 28. And that's the only ratio of sides that I have, because I only have 28 on triangle EFG. So then I look and I say, okay, well, now it all depends on what the question is asking. And since there is no real question here, I could say, okay, well, if I wanted to find GE, so if my question was find line segment GE, I would be able to say, okay, well, AD is GE's partner. So again, I could reduce my fraction to 1/7 if I really wanted to, and that would just make my multiplication easier, so I wouldn't have to multiply 6 times 28 and then divide by 4. And I would end up getting 42. So I would know that GE is 42. And then I could be like, oh, okay, you know what? I don't really necessarily want to find GE, or I already found GE, let me now find GF. I could either use my 4 to 28, which I already used once, and say 4 to 28 is equal to 5 over x. Otherwise, 1 over 7 equals 5 over x. And what I'm finding now is GF. Because I already found GE, now let's say I want to find GF. X equals 35. I could use any of the ratios to find any of the other ratios of sides. I just have to be very careful when I'm setting up my proportion to set up one ratio with information of corresponding sides. Sides on different shapes that are similar to each other. And then once I have one pair of sides where I know both measurements, then I can set up a number of different proportions to find the other measurements. So here are 2 examples of scale drawings. I know we've talked a lot about scale drawings in the proportions unit. Now we're going to be looking at how to apply using an actual ruler to doing this. We're going to do that a lot in class. Just going to remind you that when you're writing proportions with applying them to scale drawings, you're always going to look for the scale. And the scale is going to be the constant ratio. So for the bathroom problem, it's going to be that every 1/4 of an inch on the scale drawing of the bathroom is going to equal 1 foot when they actually build the bathroom. And if you wanted to figure out how long this wall was going to be, you take out a ruler and measure the wall on the scale and say, oh, the wall was, I don't know, 3 inches, and then that would be able to tell you how long that wall is going to be when it's actually built. And again, you would do 1/4 of an inch equals 3, and then you'd say x equals 12 feet, because it would be 12 feet when you solve the proportion. And if you looked at the map and you were trying to find the distance you traveled along I-120, it looks like I-120 is this, I just did it in white, but from Atlanta to Charleston. So I would get out my ruler and I would say that the symbol like this is 1.5 inches, and then I would measure the distance on the road from Atlanta to Charleston, and I would say, oh, that distance is 4.5 inches or 5 inches or 6 inches or whatever it was when I measured it. Notice I shrunk this picture so that this little symbol up here isn't exactly 1.5 inches, but on the original document it was. So then I would set up a proportion. I would say, well, the 1.5 over 50 is standard. It's constant. It's always going to be the case. 1.5 inches on that map is always going to equal 50 miles in real driving distance. And if I were to measure the distance on the map from Atlanta to Charleston to be like 5 inches or 6 inches or whatever, let's just say 6 inches, then I would be wanting to find the actual miles. And I would just do 1.5x equals 300. And from here I would just divide by 1.5. The beauty of this now is that you get to use calculators, so you don't have to actually do the fractional division, but it ends up being 200 miles. So just remember that we're taking the next step and we're actually going to have rulers and we're going to be measuring and finding actual distance, but that's the only new addition, and we all know how to measure using a ruler. So now it's just applying measurement and our ability with proportions to find actual distances.